first thing is a couple definitions. First one is flow rate, also called volumetric flow rate. It's the volume of fluid flowing. So Q is the integral of V dotted with dA. This is the general version of volumetric flow rate. A lot of times it can be simplified because a lot of times I have a constant velocity, so same velocity through the entire area, and also perpendicular to that area. So when velocity and area are perpendicular, V dotted with dA is just V times A, and then the velocity being constant, that integral just becomes the integral over the area, which is just area. So my flow rate in that case is just velocity times area. I can actually use this to define an average velocity. So again, if that velocity is not constant, I have to find it this way. I can find the average velocity flowing through that area by taking the flow rate and dividing by that area. Another similar quantity is the mass flow rate. So this is the amount of mass flowing through a certain area in a certain time. So m dot, integral over whatever area I'm dealing with, density times velocity dotted with dA. Again, you see from this, very similar to the volumetric flow rate, but now multiplied by density. So again, if rho is density, I can pull that out of the integral. I'm just left with rho times the same integral we had for volumetric flow rate before. So m dot is rho times q. And again, similar to the last one, if my velocity is constant, I can pull it out. If it's perpendicular to my area, v dotted with dA is just v times a. If it's not perpendicular, you have a cosine theta in there. But if it is perpendicular, m dot is just density, velocity times area. A couple other definitions. So my system is basically some mass of fluid that I care about for some reason. So I have all these particles of fluid. I care about all those particles. So when I look at that system and see what happens to it, a similar scenario is something called the control volume. So in control volume portion of it, I care about a certain volume that fluid occupies. So for example, I have this sort of jet engine shaped object. My control volume has a control surface around it. So my control surface is red dashed line. I care about control volume. I care about all the stuff inside this volume at a certain time. Now that could change. I could have different fluid coming in and out. So I could have fluid coming in, fluid going out, but all I care about is whatever's inside there at any given time. Unlike a system, I would care about, I have some fluid here, and I'd follow the fluid all the way through. Control volume, I just care about that part of space, essentially. Other definitions are extensive and intensive properties. So an extensive property depends on the amount of matter, the amount of stuff I have. So something like mass is going to depend on how much stuff I have. The more stuff I have, the more mass it's going to have. Energy depends on that as well. Bigger something is, more energy it's going to have in terms of kinetic energy. Intensive property is the opposite. Doesn't depend on how much stuff there's there. Something like pressure. The air pressure in this room, doesn't matter if I'm talking about this entire room or just a little chunk of air in my hands. Air pressure doesn't actually matter. How much stuff I'm talking about. Velocity doesn't matter. Doesn't matter if I have a small car or a big car, or if I'm talking about the entire car or just me in it. We're all going the same velocity. So those are intensive properties. And then many extensive properties can be found by taking an intensive property, multiplying it by mass. So the example I had before, velocity. If you take velocity, multiply it by mass, you have momentum, and momentum is an extensive property. So that happens a lot in a lot of cases. Take an intensive property, multiply by mass, get an extensive property. So now what I want to do is consider some general intensive property, little b, and its corresponding extensive property, big B, and corresponding meaning that big B I can find by taking little b and multiplying it by mass. So now I want to know how much extensive property I have, capital B, in some control volume. The way I can do that is take little b times dm, integrate over the control volume. dm, d mass, is density times dB for my control volume. So to get the amount of B I have, big B, in my control volume, integrate my little b times density over that control volume, and that gives me the answer for that. So now I want to consider a certain system moving through a control volume, such as the one I've drawn here. So I have some sort of tank with some pipes going in and out, flow coming in, flow going out. I have my system is this green fluid, so at time t, green fluid is this entire rectangular section, and this guy down here at time t plus delta t, entire rectangular section, and that part up there. And then my control volume is just this rectangular section. So I have some control volume, just this rectangular section in both cases. And I want to look at what happens to my system, my green fluid, from time t to time t plus delta t. So basically I want to know, in terms of my system, how much B do I have? So for this green part, B of my system is whatever B I have inside my control volume, so BCD at time t. And also consists of this little area, so whatever B is contained in this little amount is delta B in. In terms of time plus delta time, this later time, the amount of B that I have in my entire system, so again the green part is whatever B I have in my control volume at this later time, and then again I have some little amount of B in this area up here, so that's my total B in my system at that point. And then what I'm interested in is the rate of change of B, so how does that property B change from this situation to that situation? And so simple definition of derivative, I take my B at time plus delta time minus B at time t, divide by delta t, limit as delta t goes to 0. That's my rate of change. So using these two in there, so we get derivative of B with respect to time. The limit t goes to 0. I have BCB, t plus delta t plus B out, then minus BCD at t minus delta B in. Rearrange them. So this first two terms is just simply the definition of derivative of the B in my control volume. And then in terms of B out over delta t, I'm going to call that B dot. So basically just the time derivative, how much stuff's coming in. Same thing for B dot in, how much B is coming in per unit of time. Another way I can write that is I know that B in my CV is the integral of little b rho dv. So this guy is the derivative of the integral of my control volume, b rho dv. Then in terms of going in and going out, I can replace that by an integral over control surface of b rho b dotted with dA. So b dotted with dA takes care of things coming in and out. And like before, what we saw for volumetric flow rate and mass flow rate, I have this v dot dA term. If velocity is nice and constant, area is perpendicular to that as well. Velocity times area just come out in this form, so I just have b rho va. Anytime I have a flow going out of a surface, my area and velocity are in the same direction, so that's positive. Anytime I have fluid coming into my control surface, my velocity and area are opposite directions. So opposite direction, essentially again, cosine of 180 degrees gives me a minus sign. So whichever way you want to think of it, whether it's cosine of 0 or 180, or out is positive, in is negative, either way. But you just have b rho va out, all positive, b rho va going in, all negative. So general form, these guys are called Reynolds transport theorem, and now what we can do is we can apply that to any intensive property B. So I can take some intensive property B and get basically a equation for some extensive property. So we're going to do that for the simplest case next. So the simplest case I was talking about is if little b equals 1. If little b equals 1, then big B represents mass, because big B is little b times m, so 1 times m is just mass. So what I have for Reynolds transport theorem is d big B dt, so dm dt, because that's what big B is d by dt integral over control volume of little b, which is just 1, rho dv, plus integral over control surface of little b, again just 1, rho v dotted with dA. Then what I know from this equation is that I have a system. System can't lose or gain mass. That's conservation of mass. So because my system cannot gain or lose mass, this derivative has to be 0. So because that derivative has to be 0, these two things have to add to 0. And physically what that means is I have some mass in my control volume. I have some mass coming in or out. The change of mass in my control volume has to equal whatever net mass comes in or out of the control volume. If I have a situation where the mass in my control volume is constant, situation where this occurs would be something like incompressible flow through a pipe. So I have pipe, velocity coming in, velocity going out, density is not changing because it's incompressible. I have some control volume here. Whatever the mass in that control volume is at any time has to be the same, because it's not like there's a leak in the pipe, hopefully. So in this situation, my first integral here represents the mass. Derivative of that has to be 0, because the mass in my control volume, red box, is not changing. On left with is the second term, equals 0. Remember, the second term really means flow rate, but it could be flow rate in or out. Flow rates in are negative, flow rates out are positive. So this is basically mass flow rate out minus mass flow rate in. Move mass flow rate in the other side. Mass in equals mass out, which again makes perfect sense in terms of conservation of mass. So example of this guy, I want to find the flow rate at point 2 in this pipe down here. So I have a pipe at point 1, 6 meters per second coming in, point 3, 4 meters per second coming in. Diameter of this pipe down here, 4 meters. Diameter of that little pipe sticking out is 2 meters. And you want to know what the velocity is over on this side. How fast is fluid coming out that end of the pipe. So the solution to this guy, I'm going to use conservation of mass, because mass obviously has to be conserved in my pipe. So the conservation of mass equation that we just derived, d by dt, integral over my control volume, rho dv, plus integral over my control surface, rho v dotted with dA equals 0. Now, first thing you want to do in any of these problems is actually pick your control volume so that you can evaluate these integrals, because without knowing the control volume, you can't do that. So this is a bit tricky because it's up to you to pick the control volume. You can pick it to be wherever you want. Just some things make life easier when you try to do the math. So little hints to make the math easier. First hint, anytime you pick the control volume, make the velocity perpendicular to area. So anytime a velocity comes in, you want to make, or out, you want to make your control surface perpendicular to that. So I'm going to make one perpendicular right down here to that velocity, perpendicular over there to that velocity, perpendicular down there to that velocity. That gets rid of the cosine, so v, any vector dot product has the cosine of the angle between them. This means that the angle between them is 0, so that is just v times the area. Other thing is, hopefully you have a constant velocity. Constant velocity, this integral just becomes v times area, so that makes your life easy as well. And then last thing you want to do is, if you look at the first term, I have a time derivative of the integral of control volume, rho and dv. So basically, this time derivative means this first term is going to be 0 unless either the density or the volume change in time. And a lot of these problems are incompressible. So if it's incompressible, the density is not changing in time. So the only thing that could change in time is my control volume. So if your control volume changes in time, this term's not going to be 0. But if you pick a control volume that doesn't change in time, this term will always be 0, make your life easier. Now there are certain situations where it is useful to have a change in control volume, but they're not that many. Things like rockets taking off, that does actually help, but most scenarios it doesn't help, so not changing control volume is usually, if you can get away with it, is the way to go. So this is my control volume, as I said, perpendicular to all my surfaces where it flows coming in or out. What happens in the inside doesn't really matter too much in terms of the analysis, but perpendicular, following all my hints, not changing in time, I'm going to stay like that. So with that control volume, again, not changing in time, so this first term goes away. Second term, I have rho v dotted with dA. Again, because velocity, density are all constants, and pull them out. Because velocity is perpendicular, basically this just turns into rho VA anytime I have something going in or out. So at point 1, I have stuff going in. Remember, in is negative, so negative rho 1 V1A1. I have stuff coming out at point 2, so out is positive, rho 2 V2A2. And then stuff coming out at point 3, so rho 3 V3A3. And all that equals 0. Then I also know that the fluid's incompressible. So incompressible means my density is not changing. Density at 1 equals density at 2 equals density at 3. So these densities, I can just divide by that density, all go away. And then I want to solve for my velocity v2. So solve for v2, move v1a1 to the other side. V3A3 the other side, so V1A1 minus V3A3, then divide by A2 using my equation. And now I know all these numbers, so V1 is 6 meters per second, area 1, pi over 4 d squared, so pi over 4, 4 meters squared. V3, 4 meters per second. A3, again, pi over 4 d squared, so pi over 4, 2 meters squared. Then divide by my area, pi over 4, 4 meters diameter over there at point 2. Gives me an answer of 5 meters per second as the outflow rate at point 2 for that pipe.